We're looking at problem solving with trigonometry, and there's three concepts that we're going to focus on here. The first being the properties of isosceles triangles. So you have the apex, which is that the one opposite the base, and you have the base here, which is the side that is not equal in length to the other two. Okay, and we're going to look at an example that uses that. We're going to look at the properties of circles and tangents. So this links back to previous work we did, where we said if we have a chord there, then the radius joins that chord. What we have is an isosceles triangle there, and that chord has been bisected by those right angles. And our definition of a tangent, this line here is the tangent. It also continues. A tangent will meet a circle at right angles to the radius. Here's the first example. We have a roof shown in brown there, and it has a pitch of 16 degrees. The pitch is essentially the angle of elevation. Okay, so what is an angle of elevation? Well, an angle of elevation is where, that's an eye, we look straight ahead and we look up to see an object. The angle of elevation is that angle through which you turn your head or move your neck, if you think of it that way, to look up at an object. An angle of depression, which we'll look at in the next example, you still start by looking horizontally, but this time you look down until you see an object. And that angle in there, that angle through which you turn your head to look down at the object, that is the angle of depression. How does that relate to this particular example? So we have our angle of depression there, and what we're going to do is form a right angle triangle. That right angle triangle, that perpendicular height that bisects the beam, that would give us the height of the roof. These lengths are equal. So if we just concentrate on one of these triangles, then we have a right angle triangle where we've got the adjacent, which we want to find, the opposite, which we actually don't really care about here. We don't want to know the height of the roof. We're asked about the length of the horizontal beam, and we've got the hypotenuse. So we're going to use cos theta equals adjacent over hypotenuse, the cosine ratio. Theta is 16, the adjacent is x, the hypotenuse is 9.4. So when we multiply both sides by 9.4, we get that, and that gives us an approximate half length of the beam of 9.036. But that's not the final answer, because we want to know the length of the beam, which is 2x. And when we do 2 times 9.036, we get approximately 18.1 meters to 3 significant figures. Here's the next example. John has an eye height of 1.5 meters. From the top of a cliff, he sees a boat at an angle of depression of 40 degrees. If the boat is 1 kilometer out to sea, determine the height of the cliff. So, with all of these worded problems, we want to start with a diagram. So we have a cliff whose height we do not know, and we have John standing on top of the cliff with an eye height of 1.5 meters. That h is referring only to the height of the cliff. The angle of depression. So John is looking straight ahead. There is a boat here. He looks and he sees the boat, and he has to turn his head through 40 degrees down in order to see the boat, which he knows is 1 kilometre out to sea. One thing you have to be very careful of is that that is in metres and that is in kilometres. So we actually need to label this as 1,000, or John's eye height, divide that by 1,000 to convert it to kilometres. So now what we have is a right-angled triangle shown here. There's the right angle, but we don't have an angle inside that triangle. You have two options. You can either go here, which would be 50 degrees, okay, because what we have up here is a right angle. 40 plus what gives us 90 has to be 50. Or we can label this as 40, because what we have here is alternate angles. So the angle of elevation from the boat to John is equal to the angle of depression from John to the boat. Alternate angles, the Z rule. So it does not matter which one you choose. I am going to work with this angle in this example, which makes this the adjacent and this the opposite. And we do not care about the hypotenuse of this triangle. So therefore, tan of 40 is equal to the opposite, which is all of that. So the opposite of this triangle, the opposite side, is h plus 1.5, and the adjacent is 1,000. I'm now going to multiply both sides by 1,000 and subtract 1.5. That is an exact value, but we don't often leave trig ratios in that form when we evaluate them. So if I type that into the calculator, making sure it is set to degrees, then we get approximately 838 meters to 3 significant figures. Circle theorems. So what we have here is a point P that's 9.5 centimeters from the center of a circle. So that's that bit of information. The circle has a radius of 2. All right, I'll come back to that. We want to find the angle between PC and the tangent. All right, the tangent is this line here that I've just gone over in blue. So because we know that a tangent meets the radius at right angles, that informs us where to place the radius, because obviously the radius is 2 in all directions, but we want the one that meets at right angles to that tangent. So there's our triangle. We're finding that angle. So it's pretty straightforward. From here we have the opposite and we have the hypotenuse. We're not interested in the adjacent. We could find its length using Pythagoras if it asked us to. but we don't need that. So sine theta equals opposite over hypotenuse. Therefore, theta is equal to, and we call this the inverse sine of 2 over 9.5, or we can write arcsine. Arcsine is a more archaic method of writing this, but it avoids the ambiguity of the -1. And when we evaluate that using the calculator, we get to 3 significant figures that theta is approximately 12.2 degrees. The important thing here is setting up that diagram.